Hi, I'm Bob. We will solve the computer exercises for Chapter 14, Advanced Panel Data Methods, in the textbook Introductory Econometrics, a Modern Approach, the 7th edition by Professor Jeffrey Woodridge. We will use Stata to find answers to the computer exercises today. Let's look at computer exercise 1. The data on rental prices and other variables for college towns are for 1980 and 1990. The idea is to see whether a stronger presence of students affects rental rates. The unobserved effects model is as follows. It relates rental prices to the city population, average income, and student population as a percentage of the city population. In Part 1, we estimate the equation by pooled OLS and report the results in standard form. What do you make of the estimate on the 1990 dummy variable? What do you get for beta 3 hat? The pooled OLS estimation is as follows. The coefficient on the year dummy variable is 0.262. It suggests an increase in rental prices over time. Holding other variables in the model fixed, the rental rates in 1990 were 26.2%, or accurately 30% higher than in 1980. The estimate for the student population is 0.005. It implies that if the student population increases by 1 percentage point, the rental prices will increase by 0.5%, holding other variables in the model constant. In Part 2, we will answer whether the standard errors in Part 1 are valid. It is not valid because the composite error term contains a city fixed effect and results in serial correlation. The usual standard errors are valid based on homoscedasticity and without serial correlation. In Part 3, we difference the equation and estimate by OLS. Compare your estimate with that from Part 1. Does the relative size of the student population appear to affect rental prices? The first difference equation is as follows. The estimate for the coefficient on the student population becomes 0.011. It is statistically significant at the 1% level. If the student population increases by 1 percentage point, the rental prices are estimated to increase by 1.1% on average, after holding the other variables in the model fixed and controlling for the unobserved city fixed effects. The effect is more than double that in the pooled OLS. In the last part, we estimate the model by fixed effects to verify that we get identical estimates and standard errors to those in Part 3. We estimate the model using the fixed effects method, that is, the milling over time for each unit. In Stata, we use the xtreg command with the FE option to do the panel data fixed effects estimation. Before using the xtreg command, we should specify the panel variable and the time variable for the panel structure using the xtset command. We let Stata know that the basic unit of the panel data is a city, and the time dimension is a year. We can compare all the estimates from the above 3 methods in a table. We see that the fixed effects estimates and standard errors are identical to those using the first differencing method. Notice that the intercept in the first differencing equation is the coefficient on the year dummy. Let's do computer exercise 2. In Part 1, we re-estimate the unobserved effects model for crime in example 13.9, but use fixed effects rather than first differencing. Are there any notable sign or magnitude changes in the coefficients? What about statistical significance? We can estimate the model with the first differencing method and the fixed effects within transformation approach. Remember to specify the panel data structure using the xtset command in Stata. The county is the basic unit, and the year is the time dimension. We store the results with the estimates store command and compare the estimates in a table with the stab command. We see that the signs and the significance of the coefficients do not change. For the significant estimates, the effects from the fixed effects are slightly larger in absolute values than those from the first differencing. For example, a 1% increase in the probability of arrest is predicted to lower the crime rate by about 0.33% from the first differencing, and the effect is about 0.36% from the fixed effects. In Part 2, we add the logs of each wage variable in the dataset and estimate the model by fixed effects. How does including these variables affect the coefficients on the criminal justice variables in Part 1? We add the 9 wage variables to the model and estimate the model with fixed effects time demeaning method. We compare the estimates for the criminal justice variables and find no substantial change. The magnitude and significance are similar. In Part 3, do the wage variables in Part 2 all have the expected sign? Explain. Are they jointly significant? Some wage variables have positive signs and some have negative signs. The F statistic for their joint significance is 2.47 and its p-value is 0.009. The wage variables are jointly significant at the 1% level. Let's find answers to computer exercise 3. For this exercise, we use the dataset to determine the effect of the job training grant on hours of job training per employee. The basic model for the 3 years is as follows. In part 1, we estimate the equation using fixed effects. How many firms are used in the fixed effects estimation? How many total observations would be used if each firm had data on all variables for all 3 years? We use 390 observations in the fixed effects estimation. There were 135 groups. In other words, there were 135 firms in the fixed effects estimation. It will be 135 times 3, 405 observations if the 135 firms have data on all variables. In part 2, we will interpret the coefficient on grant and comment on its significance. The estimate is 34.23. It is statistically significant at 1% level with a t-statistic of 11.97. The job training grant is estimated to increase 34.23 hours of job training per employee on average, holding the firm size fixed and accounting for the firm fixed effects and the year fixed effects. In part 3, is it surprising that the lag grant variable is insignificant? Explain. It is not surprising because the last year's grant was for the last year's job training and has little to do with the training this year. In part 4, do larger firms provide their employees with more or less training on average? How big are the differences? The estimate is minus 0.18. It implies that if a firm has 10% more employees, the average hours of training will drop by 0.018 hours. It is practically tiny and statistically insignificant. Let's find answers to computer exercise 4. In example 13.8, we use the unemployment claims data to estimate the effect of enterprise zones on unemployment claims. The model that allows each city to have its own time trend is as follows. AI and CI are both unobserved effects. It allows for more heterogeneity across cities. In part 1, we will show that when the previous equation is first differenced, we obtain the following equation. Notice that the differenced equation contains a fixed effect, Ci. We can write down the equation at time t and t minus 1. The first differencing leads to the result. In part 2, we estimate the differenced equation by fixed effects. What is the estimate of beta 1? Is it very different from the estimate obtained in example 13.8? Is the effect of enterprise zones still statistically significant? We apply the fixed effects method to the first differenced equation. In example 13.8, we include the year dummies to capture the year fixed effects, so we also include the year dummies here in the model. We estimate the first difference equation by OLS in example 30.8, but by fixed effects here. We can store the results and compare them in a table. We find a slight difference between the estimates. The estimate of beta 1 is minus 0.182 using the first differencing measure. It is minus 0.192 using the first differencing and the fixed effects measures. The former removes the city-specific heterogeneity, while the latter removes both the city-specific heterogeneity and the city's own time trends. The enterprise zone effect on unemployment claims is economically large and statistically significant. The presence of an enterprise zone causes about a 19.2, or accurately 17.5% fall in unemployment claims. We have done part 3. Let's do computer exercise 5. In part 1, we will explain why dummy variables for occupation might be important omitted variables for estimating the Julian wage premium in the wage equation in example 14.4. We can write down the omitted variable bias formula. Suppose we omit x2 from the model, the OLS estimator beta 1 hat is biased, and the bias depends on beta 2 and the correlation between x1 and x2. In other words, if the omitted variable affects the outcome variable and it also correlates with explanatory variables in the model, then the OLS estimator beta 1 hat will have a bias. For this problem, occupation is the omitted variable. It is a determinant of the outcome variable wage. Julian participation is different between occupations, which means they are correlated. So occupation dummies are important omitted variables for estimating the Julian wage premium in the wage equation. In part 2, if every man in the sample stayed in the same occupation from 1981 through 1987, would you need to include occupation dummies in a fixed effects estimation? Explain. There will be no variation in occupation within each man over time. The occupation variable is time constant. It will be removed in the fixed effects estimation along with the individual fixed effects, AI. Or we can think of it this way. The fixed effect AI contains all time constant variables, including occupation. So we don't need to include the occupation dummies in a fixed effects estimation. In part 3, we include 8 occupation dummy variables in the equation and estimate the equation using fixed effects. Does the coefficient on Julian change by much? What about its statistical significance? We add the 8 occupation dummies to the model and estimate the equation using the fixed effects time demeaning method. Since occupation is not time constant in this sample, we can include them in the model. The coefficient on Julian does not change much. They are almost the same. it is still statistically significant at the 1% level. Thank you for doing the computer exercises with me. See you soon. Thank you for watching this video and subscribing to my YouTube channel. See you next time.